This is going to be video part 1, getting ready for our weather and water final exam. At any point, we could also go back to any of the other water and weather videos to kind of help yourself review over a topic. These are all things that we've already gone over, so I'm going to reference back to labs and experiments that we've already done, and these are worksheets and papers and notes that you guys already have on these topics. So we're going to start off by looking at what is a molecule. And a molecule is going to be the smallest particle that we can still call that object water or carbon dioxide. So when we break things down, if we were to cut water into the smallest piece we can, which would be 2 hydrogens and an oxygen, that would be a single molecule of water. If we were to make it any smaller than that and try to cut it down more, we'd be getting down to just random atoms that are on their own. So the smallest we can get down to something and still call it that object. Water is a great example for that. Again, would be the molecule. Getting smaller than a molecule, we're getting down to the size of atoms. So looking at the next thing, we're looking at what is a meteorologist and weather and climate. So when we talk about a meteorologist is a person who's going to study what weather is and studies weather and its effects on the atmosphere and on the earth. Okay, the difference between weather and climate. Weather is going to be the atmospheric conditions that are taking place around us. Weather is what happens today, tomorrow, the next 5-10 days. Beyond that, we start talking about climate, what we expect to happen during a certain season, or our expectations over a longer period of time. So the easy way to remember that is climate is what we expect and weather is what we get. Climate is our expectations again for the season. So in the summer we expect it to be warm, where we can wear shorts and t-shirts and we don't need to worry about putting on jackets and layers of clothes and it's snowing. That's climate. Can we get cold days in the summer? Yes. Same thing in the winter. We know we need to put layers on, but every now and then we get a warm winter day where it gets up into the 60-70 degrees and we don't need jackets for a day or so. That's weather. Climate is our expectations, or what we think that seasonal weather is going to be like, or that season is going to be like. We also look at next the atmosphere, and the atmosphere is the layer of gases that surround the earth. When we talk about the atmosphere, we look at the different layers of the atmosphere, and the troposphere is the layer of the atmosphere where we have all of our living things, and that's also the layer that weather takes place in. So that's the layer that we focus on. We really don't have to worry about clouds forming in other layers. We don't have to worry about life existing in other layers of the atmosphere. So we spend most of our time focusing on the troposphere. Not saying that the other layers of the atmosphere, the stratosphere, the mesosphere, and the thermosphere aren't important. They have very important functions for the Earth. For example, the stratosphere has the ozone layer, which protects the Earth from UV rays from the sun and filters out a lot of that ultraviolet cancer-causing radiation from the sun. The mesosphere causes meteors and asteroids to burn up. The exosphere and thermosphere is where we have ionized particles that glow, and that gives us our aurora borealis, along with the magnetic field from the Earth. Interacting with those particles from the sun. So all of these layers are very, very important, but we spend most of the time focusing on the troposphere. Then we start to look at what we can do with air, and we think back to some of the labs that we did where we had the 2 balloons hanging from the straws to kind of look at air having mass, and we put air inside of syringes and we tried to compress the air, and we looked at air pressure and atmospheric pressure, and we talked about what the difference is with atmospheric pressure and how it kind of affects the surface of the Earth. And we talked about, why doesn't atmospheric pressure crush things like an empty soda can, and how air pressure would get inside the soda can. It would push on the inside and the outside of the soda can with the same force. So that's why it wouldn't have a problem there. And some of the other things, like we said, air can be compressed, it has mass, it takes up space. We talked about Charles' law, where we said that when we heat air up, it expands. Okay. We also looked at Boyle's law, where we said when we kind of change the pressure of a gas, its volume is also going to its volume is going to go down. So as pressure increases, volume decreases with Boyle's law. As opposed to Charles' law, when we heat up a gas, its volume is also going to go up and expand as well. So we kind of look at, what happens when we put air under pressure and expand it, or different pressures of the air in the atmosphere. We also then start to look at the different seasons and how the sun affects the earth. I mean, we look at the sun as the major source of energy that drives weather on earth. Without the sun, we couldn't have life. It's the most important thing. That heating that the sun causes the earth is why we could have life, and that's what's going to also have a large effect on the temperature of the earth. And with the seasons, we look at the tilt of the earth as a reason for the changes in these seasons. So without the tilt of the earth, we wouldn't have these changes in the seasons. So with that, we also look at beam spreading and solar angle, and the more direct light different parts of the earth get, they're going to be warmer. So if we have an area of the equator that's going to get a lot of direct light from the sun, it's going to be warmer than an area like the poles of the earth. And that brings in that beam spreading and solar angle. And beam spreading is the way light covers a large area of the surface of the earth, and solar angle is going to be the angle at which the light strikes the surface of the earth. So we look at how concentrated is that energy as it hits the earth. We also talked about our hours of daylight. In the summertime, the sun is in the sky for a longer period of time, and that's transferring more energy to this part of the earth, or this hemisphere of the earth. So it's going to be warmer. In the winter, we don't see the sun as much or as long, so we're not getting as much energy from the sun, so the planet's going to be colder. Then we also bring in this idea of differential heating. Differential heating is going to be how we get different temperature air masses on the planet and how we get different air pressures on the earth. So differential heating is this idea that the land is going to heat up different than bodies of water. Land heats up a lot faster than bodies of water, and because of that, we're going to get different temperature air and different pressure airs on Earth, and that's going to cause wind to move around as we get those different temperatures and pressure airs. So with that differential heating, we also look at the way that energy transfers. The sun is going to transfer its energy to the earth through radiation. So we get waves and rays of energy transferring down to the surface of the earth. We also look at, when we talk about convection and conduction as well, as different types of energy transfer. So when we look at that radiation from the sun coming down, it's going to heat up the atmosphere by shining onto the surface of the earth, and the surface of the earth is actually going to get heated from below as the energy from the sun shines on the surface and it gets re-radiated or reflected off of that surface and back into the atmosphere. And then we're going to talk about greenhouse gases, specifically water vapor, carbon dioxide, just to name a few, are going to absorb a lot of that energy, and that's going to trap that heat close to the surface of the earth. Also, we're going to get some energy transferring by conduction as the air kind of bumps in or is in contact with the surface of the earth. So those are the ways that we would heat up the atmosphere. While we're talking about light and how the sun kind of transfers its energy and light to the earth, we can talk about how we see things. We need light to bounce off of an object. So we see things through this idea of reflection. So because of reflection, if sunlight bounces off of a cup, okay, it's going to then bounce back into our eye and we get an image of a cup. If there's not light shining on an object, then we don't get any information coming back to our eye. And that's also how we see colors. So as the light shines on an object, like a leaf, the leaf is going to absorb all the different wavelengths of light that shine on it except for the shades of green, and that is going to be reflected. And as those wavelengths of green get reflected back to our eye, we see the leaf as being green, when really it's actually every other color except for that shade of green. So that's why we look at like our school colors being crimson and blue, and we say, when we look at something that's crimson like that, it would be absorbing all the other wavelengths of light except for those wavelengths that make up that shade of crimson, and that's what gets reflected back to our eye. And because that's what gets reflected back to our eye, that's what we interpret as that color, because that's what our eyes see, and our brain gets that information. So we then talk about other types of heat transfer. So like we mentioned a little bit with heating the atmosphere conduction, when we get heat transfer through contact. So we actually need two things to bump into each other in this case, or like a pot sits on a stove and is actually in contact with the element of the stove. Or when we go and reach out for a cup of ice cold soda. The soda feels cold to us because our bodies are going to transfer heat to the soda. Heat's always going to transfer from the warmer object to the colder object. And as that heat transfers from the warmer object to the colder object, in the example of us reaching out and touching a cold can of soda, the heat that leaves our body is going to leave us with the sensation that that's cold. Anytime heat leaves our body, we get the feeling that that object is cold. And conversely, if we had heat coming into our body, or we reached out and touched something and it was hot and the energy transferred from that object into our bodies, we would then feel that as being hot. So the addition, or feeling the adding of energy to our bodies, is the sensation of something being warm or hot. And when we give off energy, we feel that something is cold, or that the air is cold around us, or the object that we're touching is cold. The last type of heat transfer is going to be convection. We spent quite a bit of time talking about convection. We did a lot of different labs with convection. With convection, we bring in the idea of density, mass, and weight as well. With convection, we did some of the different labs, like the incense and smoke, where we had some smoke go into a chamber and we put some ice in there and we put a candle in there, and we got to see how warm air causes things to rise and cold air causes things to sink. And that's all based off of density. When we get warmer objects, they're going to be lighter and less dense, and they're going to be able to rise up, because colder air or colder objects are going to be able to fill in underneath them and kind of push them up easier. Colder, heavier, denser air by ice would sink, exactly for that reason. And when they sink, they're going to cause high and low pressure systems. So cold, heavy, dense, sinking air is going to create a high pressure system because it's pushing down more on the surface of the earth. Warm, lighter, less dense air is going to create a low pressure system because it's lighter and not pushing down on the earth as hard. And we're always going to get wind moving from high pressure areas to low pressure areas, and we're going to talk a little bit more about that in section 2 as we talk about different types of local wind and how air moves and how wind moves. While we're talking about the different types of density, we say that things have mass, objects have mass, or the amount of matter in something. With something like a metal, there's a lot of material pushed in there, so the object has more mass. With something like foam, there's not a lot of material inside of that, and the material is more spread out, so we'd say it's a lower density, but it doesn't have as much mass either. And with mass, we also talk about volume, and as we're talking about volume, that's the amount of space that something takes up. So the amount of space that something takes up, again, using the idea of metal, everything's tightly packed together, a lot of material in a small area, it's heavy, it's dense feeling, or it's dense. With something like a piece of foam, it's not as many molecules, but now spread out over a larger area, so it's very light and kind of fluffy. Feather, even, like, would be something that has a high volume but a low mass, and that would give it a low density. We're also going to have to, on this test, calculate density, and when we're calculating density, we're going to use the simple formula that density is equal to mass divided by volume. Mass is always going to be something that we're going to look for in grams, especially for this test. So when we're looking for our mass, we go with our mass in grams divided by our volume. Our volumes are going to be things either in milliliters or in centimeters squared. And we just simply divide the mass with the grams over the volume in milliliters. And that would give us the density of whatever it is solution-wise we're trying to find. It's going to bring us to an end of the first part of this video. So if you have any questions, either go back to old videos or stop into class and see me.